Hello, welcome to another video. Today I'm going to be talking about n-gram language models, unlocking the power of text prediction. This is a precursor to more advanced LLMs, but it's going to contain concepts that are pretty important and foundational to more advanced ideas. So we could represent words and sentences as statistical ideas, right? And we connect these probabilistic concepts to sentences. So there's some useful ideas um, that I'm going to go over in this video. One, it's conditional probability. Two, the chain rule of probability. Third, Markov assumption. Fourth, maximum likelihood estimation. And five, sampling. Okay, so if you're not familiar with these ideas, it's okay, because I'm going to be going over it pretty thoroughly for the material that's going to be presented. So let's give a solid definition of what n-grams actually are. So n-grams are simple ways to model language by looking at a sequence of words or tokens. They let us estimate the probability of the next word based on the previous ones, helping computers predict text. Understanding n-grams is important because it builds intuition about how language models work, showing how context influences word choice. This foundation is essential for grasping more advanced NLP concepts, including large language models, which generalize the same idea but with much larger context, neural networks, and subword tokenization. And we saw the idea of subword tokenization in an earlier video. If you haven't seen it, go check it out. So here's some example of n-grams. Here's a bigram, which says it's a two-word sequence, I am. Trigrams, which are three-word sequences, I am happy. And fourgrams are three-word sequences, I am very happy. So these are some examples of what n-grams could consist of. N-grams can be expressed as conditional probabilities. So the question you're asking is, what is the probability of the next word given its history? And we could express it this way. Word is the target, history is the predictors, okay? For example, the history I, how is it predict N? That's a bigram. I am, how does that predict happy? That's what we would call a trigram. Now, I do talk about conditional probabilities and other probability concepts in another video called Probability and Practical Applications. If you want a deeper idea of conditional probability and other ideas, you can check that video out. So let's go over an example of a text corpus example, a very simple one. I've already tabulated the counts, so we'll just look at that. Okay, so we have a text corpus. I'm happy occurs 50 times. I'm tired occurs 25 times. I'm learning occurs 15 times. I am spaghetti, which is completely ridiculous, but that occurs 10 times. Okay, so we're going to count H, the history of the words, and then divide it by the count of the history. Okay. So total occurrence of I am is 100 times. I am happy occurs 50 times. So the probability of happy given I am is 50 out of 100, right? Because we've got a total of 100 words or sentences, I'm sorry. Now let's talk about the chain rule of probability. The chain rule of probability is useful because it lets us judge a sentence one word at a time, instead of trying to understand the whole sentence at once. N-gram models and large language models both use this idea to predict the next word based on the words that came before it, making language prediction manageable and learnable from data. So say we've got a sequence of words W1 to W2, WT. We could decompose that. Okay, so if you look at the second term, PW1 times PW2 given W1, okay? Then the next term is the third word, right? We would have W3, W1, W2, okay? For a simple for finding the probability of four words, we would do PW1, W2 given W1, W3, W1, W2, okay? And PW4, W1, W2, W3. So you could see that it's sequentially, the first one is a unigram, the second term is a bigram, the third is a trigram, and the fourth is a fourgram. I don't know the exact Latin root. Is it quattrogram? But in any case, fourgram. We could express this in general form. That symbol that you see with the tt equals 1 is multiplication. So we're just multiplying out the conditional probabilities here. And I mentioned earlier before, if we've got two words, basically it's a bigram, right? PWT condition on WT minus 1, which is just the previous word or token. I mean, word is a better phrase for that. So bigram uses the idea of Markov assumption, which assumes that the probability of the next word depends only upon the previous word and not necessarily its entire history. So what that basically means is that the previous word, okay, captures most of the information as to its previous history. Okay, so that basically says that it could take the place of, it has as much information as its previous history. So if it went out to WT minus 2, WT minus 3, we don't need that because WT minus 1 contains all the information. Okay, so that's kind of the way to look at it. And I'll give an example. So I love eating chocolate cake. We could condition it on its entire history, right? Cake given I love eating chocolate cake, okay? Using the Markov assumption, we could say cake given chocolate, okay? So it's not a far stretch, right? Chocolate is pretty, if you're thinking about cake and chocolate, it's like I love eating, it might be redundant, okay? Because of course, um, obviously everybody loves eating chocolate cake, right? So that's what I'm trying to get at. Markov assumption states that the probability of a word only depends on the previous word, like I mentioned, okay? Here's a step-by-step bigram probabilities of the whole sentence. So this is not um, replacing the entire history, but it's going step by step. I think it's a good idea or practice to kind of decompose it, see the decomposition, and look at it piece by piece. So probability of I love eating chocolate cake would be the probability of I, the unigram, probability of love given I, probability of eating given love, probability of chocolate given eating, and then probability of cake given chocolate. Okay. The next thing we have to ask ourselves is how do we estimate the n-gram probabilities? In other words, how do we find the probability of a current word given a previous word? And we could express it in the following probability statement. Now, the answer to that would be we can use maximum likelihood estimation. And this is a concept that's heavily used and relied upon in statistics, but it's used in machine learning as well and large language models. So let's give a formal definition. Maximum likelihood estimation is a statistical method for estimating the parameters of a probability distribution by finding the values that maximize the likelihood of the observed data. In other words, it chooses parameters that make the observed data most probable under the assumed model. For n-grams, since we are dealing with words, we'll be working with discrete counts. Okay. If people are not, I believe like people that understand statistics will understand what a discrete and continuous distribution is. Discrete distributions consist of things like the Poisson distribution, binomial. Continuous distributions are like normal. Yeah, so one, okay. How do we implement maximum likelihood estimation with respect to n-grams? It counts how often a word appears in a specific context and divides how often the context occurs. Now, I mentioned about, the types of distributions, what discrete and continuous are, and I go a little bit in more depth in the following video, maximum likelihood estimation. Okay. There I cover, I think, exponential, normal distribution, binomial, and so forth. So if you're interested in having a deeper dive into maximum likelihood estimation, you can check that out. So let's continue. For a bigram previous word, wi minus 1, the current word wi, so we've got this p hat, which is an estimate, right? wi given wi minus 1, which is basically the word given its previous word, right? And then we count wi minus 1, comma wi, divided by count wi minus 1. So the numerator is how many times the sequence wi minus 1 wi appears in your corpus, and the denominator is how many times the word wi minus 1 appears at all. So here's a input for I love machine learning, I love pizza, and these are unigrams, okay? So we basically do a count, okay? And it's pretty simple. The probabilities are basically divided by the totals, right? The total of the counts. I appears twice, love appears twice, machine learning appears once each, and then pizza occurs once. So how do we express this as a bigram? Same input. We get the following table. Okay, so this time we're using two words, right? Love, the previous word is I, the count is 2, because we've got I love machine learning, I love pizza, and the probability is 1. Love machine learning, 0.5. Love pizza, 0.5. And machine learning, 1. Express this trigrams. We get the following. I love is the previous two words, machine, count 1, probability of 0.5. I love pizza, 0.5 and 1. Now training, test, and perplexity. Okay, so we're gonna have to split our corpus, right, into training and test, not to different from machine learning. And we're going to have to calculate a metric. Okay. And those familiar with machine learning, you know several metrics. One off the top of my head is MSE, that's for regression. Then, of course, you've got these classification metrics as well, right? Which is more pertinent to what we're doing. So let's say we've got this corpus. I love machine learning. I love pizza. I love deep learning. We train it on I love machine learning. I love pizza. We calculate the following probabilities or maximum likelihood estimates. The test is I love deep learning. And we get this. I love is 1, but love to deep is 0, and P deep to learning is 0, right? So because it's never seen. So equals P love given I, right? We're calculating the likelihood here, times P deep given love, times P learning given deep. So we've got 1 times 0, 0, which is 0. Okay. There is a way to not get it to 0, even because if it doesn't see them, this is going to occur where the training is not going to have seen some of the words in the test. And we could do some kind of smoothing techniques, but I'm not mentioning it here in this video. Right. The specific technique, the smoothing technique that I'm actually specifically referring to is the Laplace smoothing. Make the probability of the sentence greater than 0. So perplexity measures how confused a language model is when predicting the next word. It can be thought of as an average number of possible words the model is choosing between at each step. Lower perplexity means the model is more confident and better at predicting the text. So here's the formula, right? We're doing the inverse of the probability of the word given the context to the 1nth power. And here's the expansion of that idea. I love pizza. Probability of love given I. The probability of pizza given love. And we could do the calculation. We get 1.41. Now, in order to see like how that number fits in terms of the scale of how predictive it is, we could use this as a heuristic. So the 1 is perfect certainty, the 2 is basically flipping a coin, and 10 is choosing among 10 words, right? So obviously, as the perplexity gets larger, the more confused the language model probably is. And this is a metric that's used in models along with a host of other ones. So, well, let's talk about sampling. This is a pretty prevalent idea used in statistics as well, something foundational, and it's also important in understanding large language models. So language models' internal knowledge is best visualized through sampling, the process of generating text based on the model's probability distribution. The probability distribution is produced by using MLE, as we saw earlier. Sentences with higher assigned probabilities are selected more frequently, while those the model deems unlikely are rarely produced. And here's an example. You could see that the, of, to, in, this cumulative distribution here with the unigrams take up the bulk of the probability, right? It's a lot more frequent, and it occurs a lot more often, right? As opposed to the word polyphonic or however, you could see that the probabilities are quite small, and the likelihood of it being sampled from these are a lot less. And this is useful later on in large language models to basically understand how words are predicted. Okay. The source of this is speech and natural language processing by two individuals from Stanford University, Jarofsky and Martin. So thanks for tuning in, and hope you have a great day.